Okay, so today we are going to figure out how much power this pump is required to have in order to take this. So this reservoir of water is gonna flow down into this jacuzzi, and this pump has to pump it back up into this reservoir. And so we're gonna figure out how much power is needed to do so. It's just gonna follow this highlighted path, give or take. And then I have some measurements written down. So the height of this is 1 meter. The surface of this fluid is 9 meters from the surface of this fluid. I'm setting the top up here as 0 meters. So that means this is going to be down here at -10 meters. And so one assumption we are going to make is the steady state. This is going to be a steady state function. So that means the fluid entering the jacuzzi is going to leave at, or it's going to enter at the same rate the fluid leaves the jacuzzi. So that'll help us simplify. We're also going to be using Bernoulli's. Oh, I don't think I spelled Bernoulli right. Bernoulli's energy balance equation. And that's going to be your change in pressure over the density of your fluid plus gravity times your change in height plus the velocity of your one fluid minus the velocity of other fluid, or just like not your other fluid but your different point in height. So like here compared to here, your different location, dare I say, divided by 2. And this is just your kinetic energy equation. This here's your pressure. Potential energy equals your, this is your non-flow work. And this weird F thing, which is just your frictional heating term, which is like heat transfer. However, for this scenario, we are going to ignore it because there isn't any of these piping. This piping is insulated, so we don't have to worry about it. So let's look at the fluid entering our system. So up here is going to be 0.1, our first point. And then down here is going to be 0.2. So we're going to be looking at these two scenarios. And so we're going to start off with P2 minus P1 over density of our fluid, which is just water, times gravity of 2, which is our height at 2 minus our height at 1, plus the velocity at 2 minus squared minus the velocity at 1 squared over 2, equals our work for mass. And so plus our frictional heating coefficient. So we're going to go and kind of shave this equation down. Obviously, there's no heat transfer, so this is going to be 0. There's no work being done because it's just flowing due to gravity. There's not a pump. So that's going to be equal to 0. So the whole equation is going to equal 0. Let's go over here. Pressure at 1 is just atmosphere, so we don't have to worry about it. Our height at location 1 is 0 meters because that's how we defined it. So therefore our velocity is also going to be 0 meters because this vessel's so big. It's really negligible. So we can write this equation as P2 over rho plus gravity times our height at location 2, which is just -10 plus V2 squared over 2 equals 0. So let's look at what our pressure is. So we know pressure equals rho GH. And so we know that P2 is going to be rho times gravity times height at 2 over rho. Our rho's will cancel. And so our height at location 2, so that's just going to be how submerged it is underwater, and that's going to be 1 meter. And so you're going to have, don't forget times gravity, so you're going to have 1 times gravity minus 10 times gravity plus v2 squared over 2 equals 0, which is just negative 9 times gravity plus your velocity squared over 2, which if we do some algebra, bring over our 9 times gravity, times 2 is 18 times gravity, square root, solving for velocity is equal to the square root of 18g. Okay, so now we need to find our volumetric flow rate. We know that volumetric flow rate at location 2 is going to be our velocity times our area. And we know that area is going to be the diameter of our pipe. And so we know that's going to be velocity times pi r squared. So our equation gives us that the diameter of our pipe is 10 inches. Diameter equals 10 inches. Therefore, radius equals 5 inches because it's half of that. And so obviously we need to watch our units. And so if we do some basic dimensional analysis, we know we would turn these inches into centimeters times 2.4 centimeters. And then we would multiply that by 0.01 meters. So we would get, I believe it's 0.12, oh, oopsies, 127 meters is what our radius is. So that we will plug in. So we know that, let's plug everything in. So we know that our velocity is the square root of 18g times pi times 0.127 meters squared. And so we're just gonna keep it like that for a hot minute, and we'll come back to it once we are finding our final value. So now we need to figure out the water that's leaving our jacuzzi. And we want to be energy conscious kings and queens. And so what we're going to do is we're going to take from this point at 3 to our exiting point. We'll say that's 4. So what we're going to do is we're going to have P4 minus P3 over rho plus G times Z4 minus Z3 plus V4 squared minus V3 squared over 2 equals work over mass plus our frictional heat. Okay, so now we're gonna shave this baby down. And so this is gonna be 0 because our pipe's insulated, so we don't have to worry about it. There is going to be work done because we are using a pump. And so next, let's look at our pressure. So our pressure is actually going to cancel out because these are exposed to our atmosphere, so they're the same and they're going to cancel out, so we don't have to worry about pressure. And then also our velocity is going to stay the same because when it goes to the pipe diameter, it's not changing. And so we can ignore our velocity. So we can set G times, oh, I meant to put this as a Z3, is Z4 minus Z3 equals our work over our mass. And so let's solve for our work. Multiply mass by this onto this side. Work, non-flow work equals mass times gravity times Z4 minus Z3. Oh, sorry, this is our volumetric flow rate, pardon me. Yeah. Okay, so next, Z4 minus the change from Z4 to Z3, pardon me, is actually going to be 9 meters. Z3 is actually going to be taken, I drew this wrong. Z3 is going to be taken from right here. Okay, we'll correct as we go. This is going to be power. So our mass flow rate is what we're going to take from the volumetric flow rate that went into our jacuzzi. So this is actually our volumetric flow rate. So in order to turn it into a mass flow rate, we're just going to multiply it by the density of water. And that's just because mass or density equals mass times volume. So that's how we're going to switch between our flow rates. So we know that power equals the density of water times the square root of 18g times our area times gravity times our change in height, which was 9 meters, which we got from right here. So now let's do some calculations. So this is gonna be 1,000 kilograms per meter cubed times 18. This is velocity times 9.8 meters per meter squared per second times our area, 0.127 meters squared. Oh, this is meters per second. Sorry, it's not exact. Times 9.8 meters per second squared acceleration times 9 meters. Oh boy. So our power is going to equal, so all of these units are going to be doing some transformation. So these meter cubed is going to cancel out with this meter squared and this meter. And so we are going to get about 60,000 kilograms times metered squared over seconds cubed, which this right here is going to be our joules per second or our watt, and we can simplify our power equals 60 kilowatts, which that's just doing some quick can't pause. Okay, so we're putting power into the system, and so that has to be obviously something needs to be done with it, so we have to take power out. And so the system will heat up. In order to keep it at a steady state, we need a chiller to sort of counter that increase in temperature.